Everybody, welcome back. So we've now learned about exploratory methods for point patterns. We've learned about the differences between first order and second order effects. And we've also learned what does and doesn't constitute a point pattern, learned how important empty space is, learned how important observation windows are. So we're now sort of ready to start to take the next step and start to analyze point pattern models. So point pattern models, they describe how we assign covariates. And remember, these are spatial covariates, so they have to be defined everywhere, not only at your observed points. But we will be modeling log intensity. Because intensity is the expected number of points per unit area, it can't possibly be negative. And so the natural log is how we will be modeling, assigning covariates to our intensity through the natural log. Just a quick reminder that we can take this linear model and write it in terms of matrix notation. Matrix X is our design matrix. It's n by, looks like it's k, or n by p. Beta, which includes the intercept, is in this case a k by 1. So it's a column vector here. So I felt, as I was working through this and working with point pattern models, I felt that StatStat makes it deceptively simple for us, because all we have to do is put our point pattern object right there, and then just the usual R formula. But there's a lot that happens under the surface there. There's a lot that happens, and I want to make sure that we understand what happens. One way to understand a model that you've never worked with is to reproduce it on your own, sort of by hand. And that's what we will be doing in this lecture. So our spatial covariates, they can be quantitative and categorical, right? Something quantitative can be something like a trend in spatial coordinates. It can be something like an elevation or a gradient. It can be categorical. So you can, for example, record land use and see the difference in your intensity as far as different land uses go. They can certainly include interactions, quadratic effects, smooth effects. And the reason why is, again, how this type of a model gets fit and analyzed. Quick reminder, if we record different types of points, if you are recording different kinds of species, the presence of this species versus that species, those are not covariates. Those are actually different outcome variables. And so they are called marks, but they're characteristics of the points themselves, not of the environment around which the points occur. If you have points that you have recorded, for example, once a year, every year, you have replicated point patterns. You have the entire time window, and you have basically point patterns once per year, once a month, once a day. There are analysis methods that exist in the R package, but they're not as, they're pretty well developed, but they're not as well developed as for those for a fixed time. Okay, with that, we're gonna open up the hood. We're gonna look inside because we want to understand exactly what that R package is doing. So things are pretty easy if we have homogeneous intensity. Recall that homogeneous intensity means that we don't have a systematically varying intensity, and this corresponds to complete spatial randomness. So if you've ever worked with a Poisson distribution, you may have been working with a completely spatially random process without knowing it. So here is our Poisson. Formally, this is a PMF. It's a probability mass function. And we're now the mean mu. There's only one parameter in a Poisson. In a normal distribution, there's two parameters. In a gamma distribution, there's two parameters. In a Poisson distribution, there's just a single parameter, and that's the mean, the average number of whatever. In this case, it's points per unit area. So here's a generic PMF. We are just going to substitute our ideas about spatial point patterns into the mean, right? So it's the expected number of points. Remember, the expected number of points is lambda times the area of W. And that way, lambda is the number of points over the area of W. And n is just the number of points. If we substitute these things just pretty, directly, we get this expression right here. But if you Google homogeneous Poisson model spatial patterns, you probably won't see this at all, because likelihoods for computational purposes and simplicity are typically written where we omit everything that doesn't depend on lambda, everything that doesn't in some way interact mathematically with the thing we're trying to estimate, lambda, we're going to just disregard it. And so here, lambda is certainly inside of this E function. Lambda is certainly right there, but we can see, for example, that lambda is not in this denominator, and lambda is not in a part of the numerator. So just for completeness sake, if I go ahead and look at that second term, I'm just going to rewrite it here a little bit. So nothing I'm going to do with this term. This has lambda all over it. But now the second term, I'm going to distribute the power. I'm going to distribute the power to be lambda to the n number of points, and then the area of our observation window to the number of points. And this is all multiplication, right, guys? This is all multiplication. We can multiply things in whatever order we want. And then division, we can multiply and divide in whatever order we want. There's no addition or subtraction to worry about. So I'm going to just take the second term. I'm going to rewrite it as, I'm going to erase it now, just to be super clear. Whoops, I did not need that bracket there. All right. And then I will have times the area of my observation window to the power of how many points I have divided by however many points I have factorial. Notice that this entire term doesn't have lambda in it. And so if you're reading the book, if you're looking online, if you're following another YouTube class, whatever you're doing, the homogeneous Poisson likelihood will basically omit this term, because that contains no information about the thing you're trying to estimate, which is lambda. Okay, moving on. We can take the log of that quantity because we deal with the natural log scale. By the way, this is very similar to when we were dealing with isotropic models, and I showed you, how that isotropic model estimates, how those are produced by hand. We're sort of following the same recipe here, just with the Poisson distribution and not the multivariate normal. I promise the Poisson distribution is a lot simpler. So look, I have e to some power, lambda to some power. If I take the natural log of this quantity, my power comes down, right? So take the natural log. My power comes down, and now I have plus n log lambda. The reason why I don't have a log e is because the natural log of e is equal to 1. And so that's how we get that quantity right there. Notice that it depends on the mean number of points, right? This is just the average number of points in our window. Average number of points, let's be clear. Lambda times the size of our observation window. And then here, our log likelihood only depends on the total number of points, however many points you observe, not the location of each point. And that is because, again, we're dealing with a homogeneous intensity that does not vary systematically. All right, we're all set up for a maximum likelihood estimate. To get our maximum likelihood estimate, we're going to differentiate that. We're going to take a derivative, guys. Yeah, this is the derivative of our log likelihood with respect to lambda, the parameter we're trying to estimate. We're going to set that equal to 0. We're going to solve. So the only trick is remembering how to take the derivative of a log, the derivative in general of log of x is 1 over x. And so if we're going to apply this, yeah, derivative of that is just minus size of our window. Size of the window is a constant. It's a known constant because we assume our window is bounded fixed. N is a constant, so that comes out as well. And this, I'm applying the log rule. It's just going to be that, right? We're just applying the log rule, taking the derivative of this quantity with respect to lambda. All right, now I'm going to solve, set it equal to 0, and solve for our lambda. So add the area of our window to both sides. All right. And now I'm going to multiply, well, sort of multiply both sides by the thing we're trying to find. So I get nx. I can just manipulate that directly. All right, so multiplying both sides by lambda hat. So it goes away from here, comes out right here. And now we want to solve for lambda. So I want to make sure, and this is isolated. So divide now by the area. Divide both sides by the area of W. And I get the very intuitive result. And we like intuitive results. When I found the maximum likelihood estimate, this is just the number of points per area. Lambda is the expected number of points per unit area. So far, I've been telling you what you already know using mathematics. And that's because, again, homogeneous intensities are easy to work with. If I can use, this silly little machine, I don't have to use a computer at all. This is all very simple to work with. We could have done this 100 years ago. But you might imagine that we're very limited in assuming that something has a homogeneous intensity. The most interesting things have a inhomogeneous intensity, a spatially varying intensity. And our likelihood becomes far, far more complicated. All right, first of all, our homogeneous log likelihood only depends on the total number of points. I don't have to keep track of where the points are located. But when we have a spatially varying intensity, then we have to keep track of where the points are located. We have to evaluate our likelihood at every point because some points are far more likely than others. If I have a point pattern where things get more intense as we get from the bottom left to the top right corner, I better evaluate these points, separately from these points. So that's what this first bit here does. It's simply an evaluation of our intensity at every point. Then comes another complexity. We have this integral over our entire observation window, and we have a parameter stuck in there. Right? This is the set of all of our coefficients. This could be, a spatial trend in intensity. This could have interaction, quadratic terms. But now the thing we're trying to estimate is stuck inside of this integral. And worse, integrals are far worse than derivatives. And we also are exponentiating this integral. Why? Well, if this is this is a spatially varying mean, and that takes some effort to compute. The reason why it didn't take us effort to compute a mean here is because it wasn't varying in space. So you didn't have to keep track of the fact that, your average number of points in bottom left was not the same as average number of points in bottom right. Because this is homogeneous, this expression was the average number of points across your entire observation window. But now we have to somehow take what will eventually become a weighted average. So what we have is actually an intractable integral. No amount of perseverance will help us figure out that integral right there. So why an integral? Why would our spatially varying average be an integral? So think back to the melted chocolate. If I have a square observation window and I have some points where the intensity increases with both x and y, think back to the chocolate, putting a piece of chocolate onto every observation and melting the chocolate down and having that be our estimate of intensity, having the amount of chocolate at every point be an estimate of this spatially varying intensity. What you're actually doing is taking like a volume of chocolate at every point in your observation window. There will be more, right? The chocolate will be higher here. There'll be more material, right? This is just the volume, right? An integral you can think as, adding up the heights of area under a curve. But what we actually have is a three-dimensional curve. If you take the chocolate and melt it down, your amount of chocolate will be in 3 dimensions. So the chocolate will be higher over here. The chocolate will be far lower over here, not as much chocolate. And that will be reflected by the volume of chocolate under our spatially varying sort of intensity surface. So that's a sort of a non-mathematical, heuristic to understand what we're doing. We're counting up the volume of melted chocolate, where the volume of melted chocolate gives us the estimate of our intensity. If you don't know what I'm talking about, watch the last lecture. All right, so we will assume our points are independent. So that is a key assumption that helps us figure out this first bit. If we don't assume they're independent, then we will have to sort of figure out the intensity at every point separately. If we are able to assume that they're independent, which is a typical assumption, we can just take this product, right? And then we still have this intractable integral, which is counting up the volume of chocolate across our observation window. But really, when we take the natural log, products become sums, and exponentials go away. Powers come down. This is e to the negative, and then here is our integral. When I take the log of that, the power just comes down. So this first term really is simple. In R, you would just have a sum of something. But this term right here can't be worked out. You can't use R for it. You can't use a pencil and paper for it. So that integral needs to be approximated. How do we do it? There is something in mathematics called quadrature. And I think generally, quadrature is a method of finding area. Generally, it's a method of finding area. And that works for an integral. So what we're going to do is we're going to take our integral. We're going to figure out what the height of our chocolate is at some number of quadrature points. We're going to walk around our observation window and find the height of the chocolate. Chocolate surface is continuous, but that's what this integral does. To approximate a continuous surface, we have to use enough quadrature points. So this number m is usually pretty large. M is usually large. How large? Well, you can play around with it, right? But I'm trying to demystify everything that happens when you run that ppm function in your R package. If you don't use a large enough number of quadrature points, you're not approximating that integral well enough, and you will be biasing your log likelihood. So it's better to use more than you think you need. But of course, the actual number you need is going to be unique to whatever problem you have. So we're going to take this integral, we're going to make it into a weighted average of intensities. So what we now need, these intensities will be modeled by a set of covariates. What we now need are these so-called quadrature weights, which will serve inside of this weighted average. What these quadrature weights are going to be are areas around our quadrature points. So at the points where we're taking the approximation, basically lining up and figuring out how much chocolate we're looking at, how tall the chocolatey surface is, we can only go up and measure this at a finite number of places, and therefore we're going to weigh, we're going to sort of figure out and put a space around the places where we made a measurement, and the weights will be equal to the area around our quadrature point. And of course, then our weights will add up to our observation window. So I'll visualize this in the toy example in the next slide. This is hard to talk about with math and English, so perhaps a visual is coming up. So together, the placement of the quadrature points, the placement of the points where you're trying to approximate this integral, and the assigning of these quadrature weights is what defines a quadrature scheme, which is basically how you plan to approximate this messy integral. All right, toy example. Again, the lesson here is maybe not even fully spatial stats, is when you're working with a new model, don't be afraid to quote unquote dumb it down. Pick a toy example where you have a 1x1 square window. Yeah, that's my 1x1 window. I randomly generated a point pattern with a spatially varying intensity. So it's 10x, 10y, and as you can see, the points are clustering in the top right corner. That's where the intensity is higher. So I'm going to give my quadrature scheme. So here, arbitrarily, I'm going to have a 5x5 grid of dummy points. That's where the places where I will be approximating that integral. And we're going to put one dummy point per corner. So put a dummy point per corner and have a 5x5 grid. And these are the x's, by the way. Yeah. Every x is a place where I will be approximating that perfectly continuous, smooth integral. Every x is where I will be taking the height of the chocolate, of the melted chocolate surface. The blue, of course, is where we already observed data. So you can also think of our dummy points as representing empty space. Whoops. These dummy points represent empty space where I haven't observed anything. And how we are computing these tiles is called, and this is a tough name, but I believe the person responsible for this particular way of computing tiles was a German person. And so this is Dirichlet or Dirichlet tessellation. The way that works, a good example happens here in the top left corner. We start from every dummy and every data point, and think of there being some kind of a force wave, some kind of a shock wave that propagates out. And it stops where, and this is this line right here, where we are equidistant from both our data point and the dummy. So everything inside this tile everything inside the tile I highlighted will be closer to our data point than any other point in our W. Everything that is inside this tile, and notice that we get irregular tiles this way, everything inside this tile will be closer to our dummy point than any other data or dummy point. Everything inside this tile will be sort of, think of these as zones of influence, where you are most influenced, where you're influenced by the point that is closest to you. That defines this Dirichlet tessellation. So of course, where we have nice regular dummy points, right? This was a 5 by 5 grid that defines my quadrature scheme. I could have specified a random placement of these dummy points, but I didn't. I went with a grid because I want to be able to understand and visualize it. In a grid, you know, think of that force field propagating out. The tiles will form squares. So everything inside of this square is closest to this point. Everything inside of this square is closest to this point. So you can even count 1, 2, 3, 4, 5 on the bottom with a dummy per corner. When we are around observations, you can see that we don't have regular square tiles, right? To figure out the space that is closest to this point, you know, we get a pretty irregular looking polygon right here. Sort of think of it as the zone of influence of that particular data point. The area, this is important, we're trying to figure out our quadrature weights to approximate that integral. The area of each tile will be the quadrature weight. And it's easy to see that if I add up the areas of all the tiles, I'm just going to come back. All right, so if I add up the areas of all the tiles, I'm just going to come back to how big my original square was, because I'm just taking that space inside the square and dividing it up according to what point, either dummy or data, is my closest point. Sometimes it gives me a small square. Sometimes it gives me something that looks more like a triangle, or even more generally a polygon. So this doesn't have to happen manually, by the way. I don't want to scare you guys. This happens using code. The only thing you put in is, well, how many dummy points do you want? Where the dummy points, as you're thinking, will represent all of this empty space where you don't have anything, but certainly could have observed it. So yes, intensity increases as we get into this top right corner, but that doesn't mean that a point is impossible down here in the bottom left. Just the expected number of points per unit area is far smaller here than here. I think I've beat this horse enough. We can move on. All right, looks like that just carried over and hopefully will erase. Looks like it has not erased. Yeah, that's a problem. That's certainly a problem. Let me try and reload. I will quit sharing and reload my lecture. All right, just a small tech issue. I do apologize for the inconvenience. You guys could be imagining that tessellation right now and not looking at me. Use my computer. All right, let's reshare. Share screen. And we're going to hope that this all will work out when I process the video. All right. We just finished with this slide. Areas of the tiles give me my quadrature weights. Long story short, the way that point pattern models are estimated is what is called the Berman-Turner device. I love that name. Of course, it's named after a few people who thought of this idea. And here's the big plan. We, the analyst, set up a quadrature scheme we're happy with, and compute the weights according to what I just showed you. Divide up the zones of influence of every dummy and data point. The area of that zone gives me the quadrature weight. I'm going to set up an indicator variable. Indicator variable is something that only takes on a value of 0 or 1, that identifies data points as a 1 and dummy points as a 0. Then I will make what I call a pseudo outcome variable. So we just saw that we're going to analyze sort of representative of empty space, which is the dummy points, and the sort of filled in space, which is the points you went out and collected. Where was this particular type of fish? Where was there a collar of depth? So you're going to make a pseudo outcome variable by taking your indicator variable and dividing it by the quadrature weights. So now you have a variable, and you're going to just go ahead and analyze it as a weighted Poisson model. That's the beauty of the Berman-Turner device. Once you set up a y variable like this, you can analyze it using any software that allows you to do a weighted Poisson model. You want to use SAS? Use SAS. You want to use Stata? Use Stata. You want to use Excel? Use Excel. Might be a way to do it in Excel. Don't quote me on that. So this is just a Poisson regression model. There's almost, if you tuned into this class at number 5, at, point number 5, you wouldn't know there's anything spatial there. Remember, we assume the points are independent. So this is, again, modeling that average intensity. These are the first order effects. There's something underlying in the environment that encourages greater intensity in one place than the other place. We're disregarding any type of interaction between your points. So clearly nothing spatial. There's no variance covariance matrix. There's no spatial correlation function. This is just a weighted Poisson with a fake outcome variable. It's incredible. So what it all boils down to is you take this log likelihood and approximate it like this. Here are my quadrature weights. Here is my fake outcome variable. Here is the log intensity, and here is the anti-logged intensity. So what we're going to do is we're going to get our hands dirty. We're going to analyze it in 3 ways. We're going to analyze it using the optim function, which sort of maximizes a log likelihood. It's a general purpose software, right? It doesn't know Poisson from a normal, but it maximizes a particular function. We're going to use the GLM function in R, and then we're going to use the SPATStat R package, the fancy SPATStat R package, to do the same thing. So step 1, we're going to set up a quadrature scheme. I am repeating this because this is pretty important. How you set up this quadrature scheme will determine the area of each tile, sort of the zone of influence of a dummy and data point. And this is going to determine your weights that will weigh your Poisson likelihood. So this happens automatically, but if you let it happen automatically, you don't have any control over how this happens. How much do you want to control it? That's a different question. If you don't know what it does, if you don't know how to control it, you can't exert that influence when the time comes. So set up a quadrature scheme. You've seen this on a previous slide. The area of each tile gives me my quadrature weight. So what I have is 15 data points. That's the blue circles. And then I have 25 dummy points. Why 25? I have 5 by 5 grid, right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. There are 25 red X's and 4 dummy points one in each corner. If you add all that together, you get 44 quadrature points. That's why sample size and point pattern analysis is a weird concept, because your model actually analyzes your fake variable y comprises of both the dummy points and the data points. And so in this toy example, I only had 15 data points, but the total number of things we're analyzing is going to be 44. Why 44? 15 data points, 5 by 5 grid gives you 25 interior dummy points and 1 dummy per corner. When you add up all the tile, all the different areas of each tile, you get 1. Why 1? Because you have a 1 by 1 square. Okay. So moving right along. Next, I'm going to make an indicator variable that produces a 1 when I'm dealing with data and a 0 when I am dealing with a dummy. So the trick in R is how the quadrature weights are arranged. You don't manually play with the quadrature weights. The first few are the first n. This is the number of points, number of real points, number of data points. So in our case, the first 15 are going to get ones, right? This line of code right here. The first 15 are going to get ones, and the remaining 44 minus 15 is going to get zeros. That's how we're identifying data versus dummy. So this indicator variable, 1 for data, 0 for dummy. Finally, we just take and divide, and R makes it easy for us. Now I take my indicator variable, divide by quadrature weights, and now treat this as my outcome, my pseudo outcome. All right, that's the Berman-Turner device. Let's implement it in R. So I'm gonna go ahead and collect this all in a data frame. So let me flip to R and run through this. Here I make my observation window. Of course, it's 1 by 1. The area is 1. This is super exciting. You have a blank square in front of you. I will generate my toy inhomogeneous pattern, where here is my intensity function. I specify it right here. Here is my window. And I want just a single realization, just a single realization. Make my quadrature scheme, 5 by 5 grid. Yeah, this is just a 5 by 5 grid. Method is the Dirichlet method of determining the area of each tile. Here is what specifies that this is a 5 by 5 grid. Prove to ourselves that, why do I have 44 quadrature weights? Well, I have 15 data points. I had a 5 by 5 set of dummies. So this gives me 25 interior points, and this 4 is hard-coded because there are 4 corner points. The sum of my quadrature weights is 1. Of course, if I take up the area of each tile, I add them all up, I get the area of the observation window, which is 1. This next bit of code figures out the indicator function and the pseudo variable. Let me output that indicator function again. The first 15 are ones because that's data. The next however many through 44 are zeros because I'm dealing with dummies, dummy points. Here is where I am. I now put it all together into a single data frame. And now we can analyze it using whatever software we'd like. So run it. My intensity varies with X and Y. So I will be using the X coordinate and the Y coordinate as covariates. Here is my indicator variable. Again, the first 15 are data points. The rest are dummy points. The data and dummy points have a quadrature weight. And of course, all of these Y's are 0 because of how Y is defined, right? This Y is defined as the indicator over the weight. If my indicator is 0, my Y is 0. But the weight of each 0 and non-zero is, of course, very much dependent on how we divided this space. What is the quadrature scheme that I used? Now, you will notice, because I took a 1 and I divided it by some kind of a non-zero weight, I don't have integers here. I have 115.6. I have 126.02. I have 53.285. So although I'm going to be using the Poisson, some software will yell at you because you're feeding in numbers that are non-integer numbers. But if we make our own little log likelihood, which is what I have here, let me actually show you on the slide. It's easier to show you the similarities. So here is the approximate log likelihood using the Berman-Turner method. What I do here, I call my function the weighted Poisson function. I simply produce the log intensity through assigning all of my covariates, just using matrix multiplication. This right here, type of multiplication, is a matrix algebra operation. So X is my design matrix and pars are now a vector. And now I'm going to make my log likelihood. I have a sum. Here is my pseudo variable y. Here is my pseudo variable y. Log lambda, I just made it as a function of my covariates. Here is log lambda here. Minus, I have to exponentiate it to anti-log it, right? So I don't want to remake lambda as well for computational efficiency. So I'm just going to go ahead and exponentiate it to anti-log it. Finally, multiplied by my quadrature weight, that gives me the log likelihood. Just like in our previous unit, by the way, the trick, Optim wants to minimize whatever it is that you produce. So -1 times the log likelihood will maximize. Put everything in. My starting values are 3 just random numbers between 0 and 1. Here's the function I'm trying to maximize. I have to put in what my y is, the pseudo outcome variable, what my design matrix is. Design matrix, I'm using this model matrix function, so I can just put an R formula inside. X coordinate and Y coordinate defines how my intensity varies. Here are my quadrature weights. This Hessian is for the standard errors. Of course, we need the standard errors. All right, flip back into R. Run my, just specify the weighted Poisson function and run my Optim to maximize my log likelihood. Maximize, because I multiplied by -1. And although Optim tries to minimize, if you're minimizing something that has a minus in front of it, you are maximizing. All right, actually, I will output everything that we got. So it took 194 evaluations of the log likelihood to produce a maximum. Here is the -1 times the maximum likelihood value. Here is the estimate of the intercept. Here is the coefficient of the x and the coefficient of the y. If you compare that to 10 and 10, that's not very good. But I only used 25 dummy points for simplicity so we can point to it on a screen. And of course, what I'm trying to do now is match it across software routines, not match it to quite the truth yet. All right, so the maximum times -1 is right here. Here are my parameter estimates to keep in mind. The intercept was like 0.76, x coefficient is 1.64, the y coefficient is 1.78. I have to do something with the Hessian to produce standard errors. I don't want to focus on this too much, but here are my standard errors. I'm simply inverting the Hessian matrix, taking its diagonal, and taking the square root, because standard errors are not variances, standard errors are standard deviations. So let me sort of have these on the screen. There's my coefficients. Here are my standard errors per coefficient. Down here, I'll be analyzing the same thing, but using the GLM function. Poisson is my family. That's defines the likelihood that is being used. And here are my weights W, my quadrature weights, the area of each tile you have up on the screen. Here is my usual R notation. And of course, I'm using my pseudo outcome variable Y. Right? If I fit that, it will give us a warning because we're feeding a non-integer into a Poisson distribution. If you read these warnings, that's exactly what they say. But let's take a look. If we did the first bit right, GLM produces an estimate of 0.740, 0.7632. Very close. X coordinate, X coefficient, GLM produces 1.639. We produce 1.639. GLM produces 1.7766. We produce 1.777. Good. Standard errors, 905, 905, off by that digit. That doesn't matter. These standard errors look really, really good. Now, what GLM refuses to do for us is give us a log likelihood. I would love to show you that we've actually reached the same maximum of that surface. It gives us minus infinity because it refuses to compute the Poisson with integers, non-integers, excuse me. All right, let's analyze the same data using the official point pattern model. Remember that Q was my quadrature scheme. Yep, it's the quadrature scheme. It's even telling us that we're all set up for the Berman-Turner. It's 15 data points, 29 dummy points. Together, that makes 44. 5 by 5 grid, 4 corner points. It reminds you what you have done. And that is what we feed into this model, just ppm. Q is my quadrature scheme. Little x and little y are special variables inside of the SPATSTAT package that define the x and the y coordinate. And notice that there's a comma and a space here. So although I bet you can we probably could have run it like this. We can. There it is. Okay. It produces a lot of output, by the way. This package produces a lot of output. It tells us everything we've done. It tells us it reminds us of our quadrature scheme, reminds us of our observation window, reminds us of the variety of weights, weight on the data points, weight on the dummy points. It's not surprising that we put more weight on the dummy points because there is far more empty space than filled in space inside of this toy example. All right, here are the coefficients. These should look quite familiar. And I will just output Optim just to show you on that line to you guys. Here are the estimates. These line up really nicely with, these are often exact, but of course the starting values may have had an effect. They're very, very close. The standard errors are very, very close as well. And we, of course, will get the maximum likelihood achieved. So we're using Optim minus 1 times the maximum likelihood achieved is this number that starts with 28. Using the official model, hey, look, we have achieved exactly the same point on that log likelihood surface. We just multiplied ours by minus 1. DF equals 3 reminds us that we estimated 3 things: the intercept, the beta with respect to x, beta with respect to y. I'll leave you guys with a plot of the estimated intensity. We'll be using this a lot more in the future, but it's time for me to wrap this up. Here is my estimated intensity plot with my observed points overlaid. So the interesting bit here, again, is you can't take your observed data's points too closely as, the truth. Although the highest expected intensity was way up in this pixel, we did not observe anything there. But there's a clear pattern where there are more points in the top right of our square than the bottom left of our square. And there's a clear spatially varying intensity. You're expecting as many as 60 points per unit area in this top right and as low as 0 in the bottom left. Of course, our coefficients across all software routines, our coefficients failed miserably. If you recall, the estimate of my intercept was implicitly 0. Right, it's 0 plus 10 times x plus 10 times y. My coefficient of x, the truth, was 10. The estimate was 1.64. That's not very good. How do you make it better? Use more dummy points. Y, my estimate was 1.77. The truth was 10. Again, that's not very good. but I did get the right pattern in this estimate. Sorry about the little tech glitch. I hope you guys enjoyed the lecture. We'll be playing, looking at examples applied to real data. Now we understand what this model does. We're able to control all the ingredients that go inside. That gives us license to be dangerous with some really cool data. Hope you guys join me next time. All right. Thank you and have a great day.